To the Western Australian Museum Albany as part of our Harry Butler lecture series. Tonight we are proud to present Dr Geoff Deacon, who has a PhD, a Master of Science, a Bachelor of Science with honours, and manages the Simpson Mineral and Meteorite Collection at the West Australian Museum, and lectures in geoscience at Murdoch University. In 2000, he completed a PhD at the University of Western Australia that involved the use of microfossils to track quaternary changes in sea level off the northwestern Australian coast. He has been involved with the museum's program of collecting of megafaunal remains from the Nullarbor caves, and has been an integral team member in the research of Operation Leo, the investigation of Thylacoleo's remains in Western Australia. His qualification and research experience provides a unique ability to link biodiversity to climate and sea level from both a microfossil and a macrofaunal perspective. So please welcome Dr Geoff Deacon.
Thank you, Kath. Welcome, everybody. As Catherine has mentioned, I'm actually going to be talking today about, well, biodiversity. This Harry Butler lecture series is about the International Year of Biodiversity. So my chosen topic is to link it to climate, which is a rather hot topic, if you don't mind the pun, at this point in time. And I will be using the fields that I've got a little bit of experience with, megafauna and microfossils, oceanic microfossils from the Australian coastline. I'm going to start with a statement that you've probably seen before in recent times. Climate change is real. The Intergovernmental Panel for Climate Change has made this official, just in case we didn't realise it before. And I'm going to be looking at how real climate change is. Obviously, we all experience aspects of climate change from day to day and week to week. But I'm going to be taking a bit more of a geological approach to it, and my training as a paleontologist is going to allow me to look at fossils, in particular megafauna fossils from recent times within Western Australia, particularly the Nullarbor caves, which I've actually been down and spoken to people here on a couple of occasions before, and these little beautiful things, Foraminifera, which are calcareous organisms, or they make a calcareous shell and they float, or they work their way around the bottom of the oceans in near-shore situations. But I'll get into that, I'll get into the details of those as this talk progresses. Normal. I'm going to be talking about what is normal and what isn't normal. If we're going to be talking about what change is, we have to have a perspective from which we can actually judge it. If we look at Earth's current atmosphere, for example, we can see we've got nearly 80% nitrogen, 20% oxygen, 0.93% argon, and I've left one out there, a very important one there, 0.038% carbon dioxide. Now, carbon dioxide is the contentious one. I find 0.038 to be a rather small amount in terms of carbon dioxide. The IPCC seems to think it's a rather large amount at this point in time, and I'm going to put that into a global context. And I also want to point out that the amount of water that we have in the atmosphere, which is also very important, and I'll get to that in a little bit, it's actually very important as a greenhouse gas as well, is 1%, considerably more than the amount of carbon dioxide that we have. That's what we consider normal, or that's certainly what we considered to be normal 30 or so years ago, where there's been a lot of publicity about the fact that we're moving beyond normal at this point in time. I'm going to try and put it into a context where we can actually judge that. Earliest atmosphere on Earth had 80% water vapour, 10% carbon dioxide, small amounts of nitrogen, carbon monoxide, hydrogen, ammonia, methane, and a few other bits and pieces. So you can see that normal has changed throughout time. Obviously, at the time, the Earth was very different than it is now, but that 80% water is considerable, and it would have been a greenhouse gas at that time. And of course, 10% carbon dioxide would have been a greenhouse at that time. And of course, the Earth was warmer. So I'm going to conclude that atmospheric change is real. And that's my own term. I'm going to coin that one. As part of atmospheric change, though, I want to actually put it into the context of time. And in doing so, I want to differentiate between weather and climate. That's not a very easy thing to do. Of course, it is a measure of time. The difference between weather is a day-to-day or a week-to-week process. If we want to actually look at the difference between climate and time, we want to lengthen that. Now, where you actually put the bar between a day-to-day, week-to-week, month-to-month versus centuries or thousands of years or even millions, billions of years, that's where you have to actually scale it yourself. The IPCC, in a lot of their predictions, looks back tens of years. Sometimes they've actually moved back to hundreds of years, but it's a very short and very close point of view. They have a number of different models where they're telling us where they think the climate is going at this point in time. Most of these are computer driven, and several of them have actually been shown, as in this diagram, to be quite wrong. I will address this further in a little while. But we can conclude that temperature change is real as well. In this graph, you can see to my right, we can see we've got 2,400 years worth of temperature changes. Where we are at the moment is at this bar here, but we can actually see that in 1998 we had warmer temperatures. 1300 AD we actually had the medieval warm period. This is something that appears to have disappeared from certain aspects of the literature. In between that, we actually had a little ice age. We've got the dark ages, which were basically another little ice age. We've got the Roman Empire warm period, and 1100 BC we've actually got very warm period all the way back to 2200. So we've got cycles of temperature change, and they are something that we've been able to track with time. But again, we're getting back into climate rather than weather. We can actually see that these periods with time, these temperature changes with time have become very real. Brings us on from temperature to CO2. We have various contributions to CO2. This famous graph was put up by Al Gore in his movie An Inconvenient Truth, where he's actually shown how temperature and carbon dioxide have changed over the last 600,000 years or so. Al was a little bit naughty with this graph because he makes it look as though these two are completely parallel. But if we have a closer look at the plots, and I think most people have probably heard this from now, if we have a look at the Vostock ice cores, we can actually see that they're not completely parallel, but we actually have temperature, which is leading carbon dioxide. Think about that for a little bit. Temperature is leading carbon dioxide. At the moment, we actually think that by pumping out carbon dioxide into the atmosphere, that we are warming the Earth. All the studies that we actually have, all the geological studies, the climate studies rather than the weather studies, are actually showing us that temperature rises first and is followed by carbon dioxide. So we're saying that carbon dioxide change is real, but it's not a driver. It clearly lags temperature. I've just zoomed in it's a slightly different graph, but we can actually see that we've got temperature in the blue and the carbon dioxide in the yellow there. And this is the period from 150,000 years on the left-hand side to 100,000 on the right. And you can see that temperature is rising first, followed by a rise in carbon dioxide, and it follows all the way along this plot. So what is the big picture? Well, not only does carbon dioxide follow temperature change, but carbon dioxide at this point in time, from a big picture point of view, is actually at one of the lowest points it's ever been. This is a graph of the last 600 million years, and you can actually see carbon dioxide as this black line here. So 590 million years ago, 550 million years ago, we had carbon dioxide levels that were 7,000 ppmv. At the moment, as we reach 2011, we're actually getting to carbon dioxide levels at 380 ppmv. They've risen, certainly they've risen over the last 30, 40 years, and the major contention is that in the 1930s, before the Industrial Revolution, that we actually had carbon dioxide levels at 270 ppmv. So that we actually have a situation that is some sort of change in what's been going on throughout time in the big picture, and it's possible that we are driving some of it. We certainly pump out a fair bit of carbon dioxide into the atmosphere, but we can actually see that as we look at the big picture, there are certainly other things going on. And that's what I'm actually going to look at as this talk progresses today, and I'm going to have a look at it from a paleontological point of view, and I'm going to point out some of the methods that we use in being able to track some of these things. And that's where the biodiversity part comes in. Now I'm going to introduce biodiversity just to get the concept straight. The number of different items and their relative frequency. Sorry, that's diversity. All right. If we want to actually get into biodiversity, it's the biological variety of that diversity is the variety and variability among living organisms and the ecological complexes in which they occur. It can get a little bit more complex than that because it also brings in, biologically, we can have genetic diversity, where we're looking at combinations of genes, species diversity, the variety of species, and ecosystem diversity, so the types of habitats that we have. And of course, these things can be changed as time goes on. If we look at a timeline going back to the beginning of our Earth 4.6 billion years ago, 4,600 million years ago, we have a constant change in life. The first 1.5 billion years of which, up until 3.5 billion years, we didn't actually have any life, not that we know of at this stage anyway. We haven't found any paleontologically. At 3.5 billion years, we started to get cyanobacteria. And if you've been to Clifton Lakes or Shark Bay or Lake Wallyunga up south of Perth, you can actually find stromatolites, which are made from cyanobacteria, and they're the very first organisms that we know of that occurred on Earth. That occurred 3.5 billion years ago, and up until that stage, we don't think we had any oxygen on Earth. So the norm at that period was for there to be no oxygen, and then these organisms came along and started changing them. Oh, I'm sorry, I will comment on a couple of other things. Of course, we can jump ahead to the beginning of the Cambrian, an explosion of life. Probably not really an explosion of life. Most of the life in the Cambrian had hard parts, skeletal material, and as a result it fossilizes better than the stuff that was around before. We have found soft organisms that occurred before the Cambrian, 600 million years or so ago, but the bits with the hard parts were preserved in the fossil record. As a result, when we look in the rocks, we can actually see them more easily. We find more of them around, so it looked to be an explosion of life. There could well have been more material prior to that has well been, it's either been broken down by some sort of predators or something that's eaten them, or it's just dissolved. So you guessed it, with time we actually get a change in diversity as well. I'm now going to start looking at my chosen fields as part of that change in diversity, and I'm going to start with megafauna. I came down to Albany 2 years ago and had a bit of a talk about the animals that we were pulling out of the nullarbor. And the animal that I've worked on the most has been an animal called Thylaccoleo. Thylaccoleo, I believe to either be a killer koala, if you like, or a drop bear. And I gave a bit of a spiel about the fact that this animal was an arboreal animal. It's very similar to a modern day koala in basic aspect. It has hands, it has opposable thumbs, and we're very well convinced that it climbed trees. It has very sharp claws, retractable like a cat on its fingers. It doesn't have paws, it has hands with opposable thumbs, and I'm going to skip ahead 2 things here. The claw on its thumb would have been about 6 centimetres long. This is an animal that was probably about 120 kilos in size. So a large cat, but not the size of a lion. It's not a cat. We call it Thylaccoleo. The word thylakos is Greek for pouch. Leo means lion. So we actually think it's a marsupial lion of some sort. But I reiterate, not related to modern day cats. It's an artist's depiction of Thylaccoleo stalking through the jungle. It would have actually been an ambush predator, but because it didn't have paws, it wouldn't have been the type of predator that would be able to chase down a gazelle across the plains, for example. So we do think that it climbed trees, waited till its prey came below, and then fell on it. Drop bear. Now, think about that for a second. Did I mention that we find it from the nullarbor? Does anybody here know what the word nullarbor means? Treeless plain. So we have an animal that is arboreal, that climbs up trees for a living, that doesn't have any trees anymore. Well, at least, no, the animal we know, we lived till at least 30,000 years ago, possibly 18,000 years ago, and I've got a little bit of evidence that it could even have been around 5,000 years ago. And we now find it by dropping down holes in the nullarbor into these doline-style caves, and its current conditions are like this. It wouldn't have been doing much drop bearing at that point in time. So immediately we actually have a concept of biodiversity giving us an indication of how climate has changed within that region. We're not entirely able to put a timing on it at this point in time because the specimens that we've pulled out of the caves in Nullarbor are about 700,000 years old. We know that we've got other specimens around that come back down to about 30,000 years old. But we do know that when it was alive, it was in a treed area, and that's no longer it's no longer the case now. I'll move on to Foraminifera. Foraminifera live in the oceans. If we actually go down to one of the local beaches, we'd be able to look at a big pile of sand, something like this. And throughout that pile of sand, you'd be able to find little bits and pieces which will compose these type of organisms. This is a bit of a mixture of coccoliths and forams. I'm going to call Foraminifera forams from this point onwards, just because it saves my voice and means I might be able to pronounce it properly. Foraminifera, beautiful little animals. That's giving you a scale there. So this one here is about 0.5, 0.6 of a millimetre in size. But they're very intricate. They've got lots of nice little ornamentation, and they're a lot of fun to play with, so long as you've got a scanning electron microscope to do so. I did a lot of work on these things for my PhD. I've spent a lot of time looking down microscopes to see them. They're not part of the animal kingdom. If we actually look at the number of kingdoms that we have, We've got Monero, Protista fungi, Plantae and Animalia, and they are protists. So they are very small, they are single-celled organisms, and they live in a variety of habitats, and they tend to work a symbiotic arrangement with photosynthesizing algae. They tend to grow in a manner where they start off with small chambers that continually spiral and get bigger and bigger as the organism grows, and it tends to live in the last chamber, which has this aperture here which it can pump out its pseudopodia and survive. And mostly the shells are made out of calcium carbonate, although we can actually have shells made out of silica that have actually just been picked up off the ocean floor. And generally we separate them into two types of habitats. Benthics, that is, organisms that live on the sea floor, and Planktics, organisms that float around in the oceans. The ones that float around in the oceans are very useful for surface temperature measurements, things like that, because they are ubiquitous throughout the globe. The ones that live on the ocean floor tend to have their own specific environments. So by identifying the individual species of these myriads of variety of organisms, we're able to have a look so that we can identify certain depths, water depths, types of temperature, salinity, etc., etc. And these things have been studied for 200 odd years, and there's a lot of information about the various throughout the world. And most of the varieties that we find on the shelves of Australia are present elsewhere, but these ones are specifically Bonaparte Gulf in the north of Western Australia. So what we can actually do is look at this is a generalized section of a seashore environment. So we actually have a pelagic zone here where we don't get any of the benthic forms surviving. We have nearshore marine, all the way from the beach, getting deeper and deeper and deeper till we've come off the shelf. And from that point onwards, the only organisms that we find tend to be the pelagic ones that have been floating around in the oceans. It's because these things are actually associated with photosynthetic algae. They need to actually have sunlight to be able to survive, so they tend to remain close to the continental shelf. My task was to be able to have a look at the various different types, and I'm sorry, I apologise for this slide that you can't actually read the individual species, but you probably don't want to do so anyway. Each one of these lines is an identified species of foram, and up here we actually have water depths going from 0 down to, in this case, 120 metres. And we know the various depth range of these species, and specifically I was looking at it in terms of water depth so that we can look at the overlapping range of this particular assemblage. Now, for each specimen that I would pick up within a sample, I would have to pull out 300 forams and identify all the different types that were there and work out what the overlapping depth was, just to get a depth of that single sample. In doing that, we can actually start looking at the climatic roller coaster that we have in the north of Western Australia. And this is one example. This is one core, a 4-metre core, where I've actually managed to find an assemblage that, in this case, we have a sample at the base here that ranges from 30 to 50 metres of water depth. At this point here, you can see this one's 50, this one's about 30. So we can actually look at, throughout the deposition of this core, oldest at the bottom, youngest at the top, we actually have water depth changing in a cycle starting off. This core was actually taken at about 130 metres sea level, current depth 130 metres, but when these sediments were deposited, they were at about 40 metres. So by looking at these forams, I can have a look at the way that water depth has changed in the Bonaparte Gulf and set up a sea level chart based on it. This is an example of how these various specimens have been able to identify water depths, and I have done, in this graph I've correlated it with Chappell curves, which I will get to in a second, which indicate that sea level in the Bonaparte and elsewhere around Australia was 120 metres lower 18,000 years ago. 120 metres lower means that you could have walked to Rottnest, you could have walked to Tasmania, you could have walked to Papua New Guinea. So I was showing some school kids today Tasmanian tiger remains that we got from the mainland, and they were asking me why we actually had Tasmanian tigers in Western Australia. Well, clearly 18,000 years ago there would have been a mixing between the mainland. Well, there was no differentiation between the two. As well as being able to look at just those depths, we can look at the chemistry of those forams, and specifically we can look at stable isotopes. Even more specifically, we can look at oxygen isotopes. When we actually have, this is the modern day polar ice cap, we have an accumulation of, I'll take one step back. Oxygen isotopes come in two forms, O16 and O18. O18 is heavier than O16, so as we evaporate water from the surface of the planet and it falls as precipitation in the ice caps and remains trapped in the ice caps, progressively more and more trapped in the ice caps, we increase the amount of O16 that is locked up in the ice, so the water, the composition of the water that remains in the oceans is relatively increased in O18. What we can do is we can then look at sediments throughout the ages and look at the relative ratios between O16 and O18 and have a look at a sea level curve, constructed sea level curve, in this case for the last 80,000 years. This is work that was predominantly done by John Chappell and John Shackleton in the 80s. And as you can actually see in this case, that last glaciation that I was referring to earlier, 18,000 years ago, they actually have isotopic signals that tell us that sea level was about, in that case it says about 130. The point of doing my particular study was to actually put it into an actual context rather than a chemical context. So we can actually have sea level curves that show us when we have an interglacial period and a glacial period. And if we look at, is that us? If we actually look at this last interglacial period, this is a true slope of that last interglacial period, 18,000 years worth of data, we can see that throughout that time we've had a sea level rise that started 18,000 years ago, was fairly slow, gradually increased until it had a slope at this point here from about 10,000 through till about 7,000 years. Sea level was rising at 14 millimetres per year. Currently, the estimates of what sea level is rising are between 1 and 3, 1 and 4 millimetres. Now, the publicity would tell us that this 4 millimetres, let's say 4 millimetres just for argument's sake, I tend to believe about 1.1 actually from the data sources that I've been looking, and I've researched it pretty heavily, indicate that we're actually rising at one of the slowest rates for the last 18,000 years. It's not what we would actually call a runaway greenhouse. It's not a very high rate of increase at all. And in fact, if we actually look at the overall graph, we would say, it would tend to tell us that we are starting to get to the top, or maybe have peaked at the top, and are about to turn down into a cooling cycle rather than to run away into a continuous warming cycle. You can just have a look at that blown up. It's a slightly different graph, but it's the same data. And you can actually see that it's, even though these are the error bars, so this is the data, and this is the best data that we actually have for these type things. And you can see that we are not, certainly not getting, sea level is not rising at a faster and faster rate as some people would have us believe. The big picture. So this is how, now at the same time as being able to have a look at the way that sea level has changed, we can combine this with pollen data to have a look at the type of vegetation that we have throughout Australia. And we can find that this is our current situation, and this is what our situation was at that glacial period 18-odd thousand years ago. So that we know by looking at this particular event and previous events that we have a general association between actually having interglacials, which are warm and wet, and glacial periods, which are cold and dry. Don't ask me why I use red for cold and blue for warm, but I was having a bad day at the time. You can actually see the last interglacial, 115,000 years ago, was a warm wet phase. We've got a warm wet phase currently, relatively speaking. There was this point here, which is a relative high. It's not overly convincing, but as we look at the same sort of isotopic data that I've actually been showing you for oxygen isotopes, we can have a look at the last 800,000 years, and we can see a continuous pattern that goes from interglacial through slowly down to glacial, interglacial, slowly down to glacial, which tends to be a very steep rise up to the warm periods and a slow fall down to the cool periods. 800,000 years of which, if we look at our current situation, it's not any different from anything that we've had before. We're not in some sort of runaway greenhouse from a big picture point of view. It gets even better. The upper graph is the last 2.5 million years of data. And you can actually see that these cycles are a little bit more compressed, but we've just got glacial, interglacial, glacial, interglacial, all the way along. Some of them are a little bit higher, some of them are a little bit lower. The ones that we've actually got at the moment are not out of the range that we would expect in any normal interglacial glacial cycle. If we go even further back, we actually find that from the point 2.5 million years onwards, back to 5.5 million years, we actually start getting into the relatively warm periods. We're currently in an ice age. The geological definition of an ice age is that we have ice on continents in the northern hemisphere and in the southern hemisphere. We entered that ice age approximately 3.5 million years ago, and we can actually see that within these cycles it's gotten cooler and cooler, even though we've got these interglacial and glacial periods that cycle it. They're just parasitic within the overall trend. So what does that mean for us? Well, this actually shows where we are currently at today. 15 degrees is our average temperature, and this shows how much time we've actually spent below throughout. This is going all the way back to the Precambrian, so we're going back 3.5, 4 billion years. These are the cool times. doop, and doop. And the rest of the time we've actually spent a lot warmer than now. I think that tends to indicate that we're not actually doing anything unusual with respect to the normal cycles. We are just currently following along in the way that we always have. There are a lot of details that can be gone into in terms of what does drive climate change, but at this point in time, I'm pretty well convinced that it's not us that's doing it. Warm and wet is good. We're heading towards warm and wet. Are you ready? Thank you, everybody. I'm happy to take any questions about the topic at hand. I can't see anybody, but I'm quite happy to listen.
Is the current argument more about the speed at which things have changed? I mean, that's what we've been told, isn't it? That the rate of change recently is out of the ordinary.
The current, yes, the current change in carbon dioxide is high, but it has happened at similar rates before. And the problem with it being a problem is that there has been no corresponding increase with temperature, and geologically we wouldn't expect an increase with temperature because we've never seen it happen before. We don't actually expect carbon dioxide to be a driver of temperature change. The reason that it works the other way around is a matter of simple chemistry and physics, that if you try and dissolve gases into a liquid, you can do so at colder temperatures. The colder a liquid is, the more carbon dioxide it will hold. At our current levels, the amount of gaseous carbon dioxide that is available on this planet, 93% of it is actually held in the oceans. We are obviously in a series of global warming, global cooling phases, and as the Earth warms, the oceans are not able to actually hold as much carbon dioxide, so carbon dioxide gets released into the atmosphere, not the other way around. Of course, we are actually driving carbon dioxide into the atmosphere as well, so yes, there is a larger signature of carbon dioxide in the atmosphere, but it doesn't appear to be anything that's really going to cause us any problems.
So that would have some implications as to the pH of the oceans? Does that change the flora?
Yeah, well, the pH of the oceans have changed considerably throughout time, worse than they have at the moment. 11,000 years ago, we actually had pH in the oceans that was down to 8. Keep a mindful, there's been a lot of publicity about acidity of the oceans in recent days, in fact the last few weeks. It's not acidity, it's not acidity until it gets to 7. These are actually alkaline oceans, and they're well buffered by the amount of carbonate that we actually have in the oceans. I have some slides that I haven't actually put in this thing, but if you actually look at the White Cliffs of Dover, for example, every centimetre of carbonate that is within those cliffs has got enough carbon dioxide to equate to the amount of gaseous carbon dioxide that we have in the atmosphere at the moment. And when we actually get an increase of pH, if you were to actually drive more carbon dioxide into the oceans, but as I'm saying, we're actually degassing it rather than the other way around, it gets buffered by the carbon dioxide. And there are experiments that have been recently shown that corals don't like pH, but they're not very well set up experiments because they actually used hydrochloric acid to dissolve them. And corals don't work with hydrochloric acid, they work well with carbon. They actually use the carbon from carbonic acid to be able to grow. So I think they need to have a better look at the way that they've run those experiments. I hope that answered your question.
Yes.
Wherever you are.
Is it more like, or with the rates of carbon dioxide with the ocean warming, is there likely to be more carbon dioxide contributed by that factor than by...
Yes, look, as long as the Earth continues to warm, and it's more likely that that warming is being contributed to by the way that the Earth processes around the sun, the actual energy of the sun that changes with time, the way that the Earth wobbles. There's a number of different cycles that have all been grouped together to be called a Milankovitch cycle. And each one of the cycles that I was showing you there are referred to as a Milankovitch cycle, and they tend to occur on 100,000 and 40,000 year cycles. There tends to be a combination between them. As long as those cycles are actually driving the Earth towards warmer periods, yes, there will be more carbon dioxide thrown up into the atmosphere. But guess what happens to that carbon dioxide? We don't have to go pumping it down into the ground or trying to store it somewhere. It becomes plant food. I do actually have a slide. It just happens to be there. How's that? This is what trees. This is a study showing that that long-lived pines in the USA have, and it's a little bit complex in terms of the way they've actually done the graph, and they've measured them in terms of standard deviations of the norm. But you can actually see that in the last 50 years, you've got the growth rates of trees have been increasing considerably, and the reason that they're increasing considerably is that they've got a lot more food to be able to drive them. If you think about how a tree grows, you put a seed in the ground, and it gets water, nitrates, a few other bits and pieces from the earth itself, but the carbon that it is made up of all comes from the atmosphere. So you start off with nothing and you end up with something that is made up of 99% carbon, and it all comes from the atmosphere. If you increase the amount of carbon dioxide in the atmosphere, the trees grow more efficiently, and studies are actually showing that at this point in time they're growing better than they have for a long time. If you just allow that to occur, it will actually pull in most of the excess carbon dioxide that will be pushed out of the oceans, and this itself has occurred many times before. Keep in mind too that prior to the Carboniferous, 400 million years ago or so, we didn't actually have any trees on Earth. So there was more carbon dioxide in there. At that time, that graph that I showed you, that where carbon dioxide has been progressively decreasing with time, has occurred because of the occurrence of trees, which have changed normality. And at this point in time, humans are actually acting as a fertilizing system to allow trees to have more food.
So we just need to plant more trees.
Yeah, sure.
Trees
Happy
growing
to.
faster doesn't necessarily mean they are better though. As I understand it, faster growing trees can be weaker.
I think you'll actually find that this graph is actually looking at the amount of biomass within the tree. It's not actually saying that it's faster, it's actually saying that there is more tree being formed. So it's not that they're growing fast and weak, they are actually, there's more carbon there to actually form the bits that they have.
Does the position of Antarctica have anything to do with the current patterns in the ocean? Is that...
Yes, but the Antarctica separated from Australia 45 million years ago. So, I mean, very few of the plots that I've put up there have gone beyond that. So it's not part of the current changes. I mean, we do there as you get cycles within summer and winter ice melt and things like that, it does tend to change some of the ocean flows, but only in terms of speed and that. It's not really changing the way that we've got carbon dioxide into the atmosphere, to my knowledge.
One of the concerns that is thrown at us is the way in which the glaciers are melting, particularly in the Himalayas, and the melting ice is creating extra water for irrigation and human consumption. And the concern is that when they have melted out, or there'll be no more glacier to melt, all sorts of doom and gloom. Do you believe those glaciers are just going through a normal cycle? Or the glaciologists, can they contribute anything to the story that you're talking about?
The blue line is glacier shortening. You can actually see that this cycle of glacier shortening here started, about 1850. So yes, the glaciers are shortening, but it's part of this current global warming system that we're in at the moment. And even to actually say that it started here, of course, this is part of a much larger cycle, and there's probably an aberration where it goes this way. I don't know any further than this, but clearly, if you actually got glacier shortening in 1800, it's well before the beginning of the Industrial Revolution. This is not caused by carbon dioxide that we have actually produced. It was happening well before that.
Maybe they'll grow a bit this year after Europe and America top.
Absolutely.
The coldest one for 30 years.
Absolutely.
Maybe it's the start of it.
Yeah. But we're also in an El Nino year as well, so we're going to get some warming in the southern hemisphere. But yeah, and that's the thing, most of the time you have a look at the way that the temperatures cycle, and when it's warm in the northern hemisphere, it's cold in the south, etc., vice versa.
I honestly think that a blink a blink is a million years in the world's history, and no one's been around long enough to know what really has gone on in those years.
Well, I actually think I think you're right, and as I've sort of been trying to push in this talk, looking at the very small picture is just not giving a big enough view to be able to view it. Really, by looking at the paleontology, we can actually see what's been going on for a long period of time, and it's not out of the ordinary. I mean, it is high, it's different, but it's not anything that we haven't seen before.
And the other thing that makes me laugh, how's the tax going to stop it? The carbon tax. It hasn't stopped me from drinking wine. I can tell you that it's going to double. And the other thing, is trading carbon. You're going to go over there and grab something you can't see. You're going to take it back over here and sell it to someone that can't see it. Just imagine the corruption that's going to go on in between.
Yeah, I think. Look, I think it's getting off topic. It's not my field of expertise, but it seems that the main drivers of a lot of this publicity tend to be political.
It is.
And if you set up this carbon tax system, then governments get free money. And people are willing to pay it, and I think that's why there's been so much support, and that's why it's gotten out of hand. I've been asked on many occasions, look, okay, let's assume that this is all correct. What's the harm in actually going through with it? If people are willing to pay to reduce the amount of carbon dioxide, then why don't we just do it? And the harm is that, one, the world's economies, other than a few rich countries, are struggling at the moment. 35,000 people die of starvation every day in our current climate. If you start removing farming land to produce biofuels to fix a problem that doesn't exist, you're going to increase the amount of people that are dying on a day-to-day basis by a large amount for no reason. And I think for that reason alone, it's something we should resist. Because as far as I can see, and looking at all of the science, it's not happening. It's not a problem.
There seems to be a problem of what we might call trust in science, and the community and the ability of science to get its message across, and to avoid spurious messages being made public and fodder for political misuse.
I think the ClimateGate situation, which presumably most people are aware of, that broke last December, where it appears that certainly a number of the chief scientists within the IPCC have actually been falsifying or biasing their results in some way, is actually causing a lot of people to lose faith in science. And there's been a lot of discussion about the consensus of science that these guys have put forward for a long time, and yet true scientists don't believe in a consensus. I've been called a skeptic from so many different directions, it's not funny, but I'm proud to be a skeptic, because as far as I'm concerned, as long as I'm being a skeptic, I'm a scientist. And I think it's necessary not to just believe anything somebody tells you, but the whole world is believing this story at the moment.
How many times have they told us an egg's no good for us, then it's good for you, then it's no good for you, chocolate's good for you, then it's no good for you, then wine's good for you, no, it's no good for you. They're scientists, I think. Right? Got to be crazy.
But why are these scientists being political?
I think, it comes down to money and fame and fortune for themselves. They've become very preeminent around the world.
You hit the nail on the head. The monetary system, a global monetary system, is in such a turmoil that G20 countries are pushing this. They've all got together to get a tax, like you were saying, to help to get them out of it. That's all it's about.
Yeah. But again, that's out of my field. That's not. I'm just speculating here.
Can I take a step back and the nullarbor and the caves
Yes,
you have been studying from? What other information did you find in the caves that has helped you get to where you are now with your opinions?
Look, I think in terms of climate, and most of the studies that we've done with those nullarbor caves, and it's such a big ongoing project. I mean, we've probably pulled out 2,000 specimens of various types of animals in that time. I think the benefit of it, I mean, those caves are so beautifully designed as animal traps.
So have they been animal with the sea level at that depth at some stage, or
the whole nullarbor was
the caves to be there in the first place? River systems, or what is the driving force of the knowledge that's in them?
The megafauna that we've been pulling out of these caves date back, as far as we're aware, back to 1 million years or so. The sediments that formed, that these caves are actually forming in, were deposited 20 million years ago. So the actual formation of the sediments and then the subsequent formation of the caves, which have happened because the nullarbor is mainly limestone material, so most of the rivers flow underground. You rarely see a river on the surface, and that's what's formed most of these caves. So these are ancient systems. Most of the rivers were thought to have formed probably 7 or 8 million years ago at least. So really there's no real connection in terms of looking at the animals that we're finding in the cave systems and the sediments that actually formed them. So we're not linking that to the climatic system of that time.
Okay. So what about the arboreal
Thylacoleo, yeah. Well, again, that's been around for 5.
Where's the evidence of the taller trees?
Oh, we have lots of evidence. We actually have stalactites from these caves that have got very high carbon content in the centres, and they gradually get less and less carbon content as they get out to the more recent things. So that is giving us an indication of, one, that the times previously were wetter, and that there was more humic material around. There was a period that had that these animals did have more trees around. So yeah, that supports the fact that Thylacoleo probably was an arboreal animal.
Were they also found in Tasmania then? Because with Tasmania's tall trees and nullabor's very short trees.
I haven't heard of any deposits of Thylacoleo, but keep in mind that up until 5 years ago, we only knew of Thylacoleo from 3 sites within Australia. We do find them in Queensland. We find them in Naracoorte in South Australia, and the original one was actually found in Victoria. So
None in Tasmania?
No, not so far. But yeah, it's highly probable that somewhere along the line there'll be a cave deposit somewhere where these things are.
That's interesting that the trees are so low in stature on the nullarbor now.
At this time,
they were
yeah.
so tall to support
But even then, that vegetation map that I showed you there, 16,000 years ago, obviously they would have been unable to sustain themselves at that time. It's relatively green there now than as compared to when it was there.
I went across the Birdsville track 2 years ago to Longreach, and they got big placards, probably twice as big as your screen up there, saying that 70 million years ago this was an inland sea, and they've actually got it all drawn in the map of Australia. It came from the Gulf of Carpentaria, right down to Cooper Beatty in South Australia, and right down to Lake Eyre.
Yeah.
That was an inland sea, so it was wetter 70 million years ago than it is now. What dried that up?
Well,
Climate change.
Yeah, climate. It's all part of the climate change cycles. When we get the highest sea levels, that's when the ice caps have actually melted, and that's when you've got more water available. One, to lap against the oceans, against the continents, and two, in terms of the actual water budget. So that's when the ice caps have melted, you get more rainfall and you get wetter conditions and you get more lush vegetation. The Cretaceous, for example, was a very warm and wet period. Carbon dioxide levels were 4 times higher than they are now, and temperatures were probably 5-6 degrees higher than they are at this point in time. And we had dinosaurs living in Antarctica. And that gives us, we have actually found dinosaur remains, Cretaceous dinosaurs on a continent that now we only ever see covered in ice.
Humans wouldn't have been able to live in a high carbon atmosphere, would they?
Yeah, sure. We've had humans living for the last 4 million years in our current form, and we've lived through many high carbon dioxide levels. Yeah. Carbon dioxide's not poisonous to us.
It's actually our stimulus to breathe. So if we don't have carbon dioxide, we don't have stimulus.
Yeah, that's exactly right. It's gas of life.
We used to have very expensive real estate on the coast back then, I think.
Are those peaks and troughs normally, going back to your paleontological skills, are they normally synonymous with catastrophic events for
these small 1,000-year or 400,000, 100,000 year cycles? No, they don't tend to be associated with catastrophic events. It's relatively. I mean, I guess everything on Earth in terms of being able to survive for millions of years has grown up with these cycles. So they don't. If they've survived to this point, they're not actually seeing them as being an issue. At our current species diversity.
Peak or trough that actually marked a significant impact on the findings that you guys made?
Oh well, we've probably at the end of the tertiary that it's probably 5 million years ago. We certainly had changes in cycles. Each one of the geological periods that, and I'm going to have to find something like that one, yeah. Each one of these geological periods, so tertiary, Cretaceous, Jurassic, Triassic, something tends to happen at the end of all of these periods. That's why we actually mark them. We see a sedimentation change. Some fossils are knocked out of the system, or something comes in at that point in time. So you can see that they're fairly regular in terms of how often they happen on a large scale, because we're looking at 100 million years at this point here. So these cycles are 50 to 100 million years. So regularly we do actually have things that occur that do hammer the system. But for something like the end of the Cretaceous, when we had a meteorite impact, we had huge amounts of volcanism being pumped into the atmosphere. We certainly had severe climate changes. Different studies have actually shown that there was huge warmings and huge coolings that all happened at that same time, and 80% of species on Earth were actually wiped out at that time. And that's not that far ago, that long ago, if you actually look at it in terms of a geological context, the big picture.
How do you work out the average global temperature millions of years ago?
Oh, yeah, I don't know. There's so much input for those sort of graphs, you've got sea surface temperature, water temperature, sea bottom water temperatures, you've got troposphere temperatures, and you've got various atmospheric temperatures, as well as actually having land temperatures themselves. I don't know what the actual algorithm is for doing it, just so long as you actually keep to the same measurements as you do each one. So basically, if you're comparing, you make sure you compare apples with apples and oranges with oranges, rather than try and combine them. It's a good question. Oh, it would be calculated using computers, but no. In terms of actually looking at the older temperatures, we're actually looking at probably oxygen isotope data, tying it into the relative amounts of your O16, your O18. We can also look at carbon isotopes, there's sulfur isotopes, etc. There's a number of different proxies that we can actually use to see how the shells of forams, for example, have changed their makeup throughout the millennia.
I've said in a lot of cases with rising sea levels, it's blamed on climate change, but would it be fair to say that most of the examples would be either coastal erosion or sinking land masses, especially when you look in the Pacific? You've got a lot of coral atolls and volcanic islands, which are probably just decaying back into the sea.
Yeah, absolutely. There's both. I mean, certainly sea level has been rising. Sea level has risen now for 18,000 years. So throughout that time, there have been islands that have disappeared, and 8,000 years ago, islands would have been disappearing left, right, and centre.
I just sort of feel that a large proportion of that disappearance is
Yeah.
probably due to erosion more than anything.
There's certainly an erosion effect. If you look at the Hawaiian Islands are actually a chain of islands where we've got the continent moving over the top of a hot spot, and while there is volcanism occurring over that hot spot, everything expands and the islands end up sitting just above the ocean. As soon as they move away, as the continent keeps on moving away, that starts to cool and all the islands drop down. So if you actually if you've got Google Earth at home, have a look at Hawaii, and you will see there's this big chain of underwater islands that once upon a time were sitting above the ocean, relatively recently geologically. And in fact, you can even see where that chain of islands has changed direction as the plate juxtaposed and changed its direction, probably around about 70 or 80 million years ago. That's an example of what you're saying. Yes, it certainly happens.
Well, I think we might draw the questions. For the moment, certainly Geoff will be here to talk to you afterwards. We'd just like to say how interesting that lecture was, that it probably raises more questions than we have answers for. But again, I would like you to thank Geoff Deacon, Dr Geoff Deacon, for his very informative lecture. Right, and we encourage you to stay and have some supper with us, and you'll then have the opportunity to further interrogate Geoff with more really fascinating questions.
Yeah, bring it on.
I'll just turn the lights
Thanks,
on
guys.
so we can see.
That'll be good.